Okay, we are live.
Okay. Oh, okay. There we go. Some people are joining now. Mark, do we know how many are expected? I'm just looking at the counter. I want to give people a chance to get in, but do we have an idea of how many are registered?
We have about 75 people registered for the thing. I think people will come in or out, and some people attend, some and not others. So I would just say start. When people want to join, they join in. So we'll see it kind of go up and down as we go.
Okay. Perfect. So yeah, all right. We'll jump into it then in the interest of time. Don't want to be going over here. Good afternoon, everyone. My name's Will Russell. I'm with Panasonic Canada on the business management side. I have with me here today one of our distribution partners, John McLeod, from Nordics Inc. in Ontario. They're one of our main HVAC distributors. We're going to be kind of going through this together. I'll be driving the presentation, and then John is here to assist me with any additional information that he has on a more contractor-facing view, and can help answer any questions or comments as we go through here. So today we're going to be focusing on air source heat pumps, air-to-air heat pumps specifically, and what the opportunity that they have in Canada's residential market and what role they can play in decarbonizing Canadian residential heating and cooling. So for introductions, just a little background on myself. I've been with Panasonic Canada for about 4 years now. All 4 of those years have been in the HVAC and indoor air quality space. My primary role has been developing solutions for the North American market and how we can localize some of our Japanese products. Like I said, John is our territory sales manager for Nordics. We've been working with Nordics for about 3 years now, so we wanted to include them in this partnership here. John, I'm not sure if there's anything you want to add about yourself.
Yeah, thanks, Will. Yeah, so we're really excited. My little bit of background, I have a contracting background in that I had a company for about 15 years prior to joining Nordics. And so I think, we were going through this entire process to, sort of usher in the transition to the new heat pumps. I think I can come at it from a pretty good angle of sort of thinking like a contractor. Because I think about where we were 3 years ago to where we are today, and the transition as we usher in the new sort of era of heat pumps. And I think it's pretty amazing how far we've come in a very short period of time. But I think, Will, I'll let you go with your presentation, but I'll be happy to jump in if there are any questions.
Perfect. Well, John, I think you set us off on a really good point, touching on the transition there, because where we're going to start with this is, what's driving the heat pump adoption and where we see ourselves going. So the first thing we have to kind of ask ourselves is why heat pumps, and specifically today we'll look at why air source heat pumps. And the simple answer is, well, because we have to. For those of you who are not familiar with the Kigali Amendment and the Montreal Protocol, Canada has committed to reducing carbon emissions by 40 to 45% of our 2005 level by 2030. So as you can see, by 2021, we're a little behind in our progress, and we need to start making some good headway there. And furthering this commitment to carbon reduction, Canada will be a net zero country by 2050. So we have a very long way to go, and there's many areas that we can tackle. We're going to focus here today on residential heating and cooling. In terms of the scope of this on a national basis, Canadian residential or residences, so looking at homes and primary residences, account for about 18% of all Canadian greenhouse gas emissions. And as you can see here, 65% of that is space heating and cooling. Now we've lumped in both the heating and cooling into this 65%, but largely we're talking about heating when we're talking about greenhouse gas emissions. This is what comes primarily from the burning of a fossil fuel to act as a primary home heating system. And this is going to be the biggest target that we're going to look at today, is on how we can reduce this in both new and existing buildings. So moving forward to meet our goals, Canada currently has a home supply of about 15 million existing homes, and to come in line with our 20 or our 45% greenhouse gas emission reduction by 2030, about 75% of those existing homes are going to require some form of carbon reducing primary heating and cooling system retrofit. So when we're looking at solutions for this, we have to look at what we have currently in our existing homes and make something that makes that transition easy, because when we're talking about 75% of 15 million homes in the next 7 years, that's a very sizable undertaking. This is something that's going to be driven by federal grants and rebates and incentives. I think that's something John will add as we move through this presentation. And then the other piece of this is we have to look at our new construction. So the federal, the 2024 federal budget, as known as the housing budget, it's looking at really relieving a lot of the roadblocks into building housing and increasing Canada's housing supply, which we're in desperate need of. So moving forward, there will be regulation that limits the primary heating and cooling systems in homes to something that is less carbon intensive, and most likely we'll be looking at some form of electric system. That's one piece we'll have to look at moving forward. But in terms of this 75% retrofit rate, how does that look, and where do we, how can we provide solutions for that? When we look at the Canadian primary households and their primary heating systems from 2021, according to Stats Canada, over 50% of existing Canadian homes have an existing forced air furnace. So it's a fairly common system. You have your furnace, typically a central air conditioner, and that's ducted throughout the entire home. This is going to be one of the largest opportunities for HVAC and heat pump installers in the next couple of years, is replacing these systems as they come up either to the end of their life, or as you're being driven as a homeowner to proactively replace your system with a less carbon intense system. So this will be driven by the Greener Homes Grant, which is a national incentive for homeowners looking to transfer their current furnace or heating system to a heat pump, something less fossil fuel intensive. Excuse me. So in terms of that, we've talked about heat pumps and the need that they can serve and where they fit in, but what exactly is a heat pump, and how does it work? So an air source heat pump, it works in both ways. It can provide heating in the winter as well as cooling in the summer. And it does that by reversing the refrigerant cycle you see here on the right of your screen. We'll first talk about going through this in the heating cycle, so we all have a good understanding of how this goes, and then we can explain the cooling piece here. So this system is made up of an indoor and outdoor unit, typically a split system. And what happens here is the expansion valve will turn the high pressure refrigerant into more of a low pressure, low temperature gas that will go into the outdoor fan coil. At that point, this is where heat pumps work, is they rely on absorbing heat from the outdoor air. So as this low pressure, low temperature refrigerant moves through this outdoor fan coil, that'll absorb heat from the outdoor air, and it will continue to pass through the reversing valve in a vapor form now. So right now, as it absorbs heat, it goes from the liquid state to a heated vapor, and then it goes into the compressor. The compressor then compresses that gas, and what happens there is it increases the temperature of the gas before it's released into the home and the inside coil. Once it's in the indoor coil, That's where, using the fan, you will distribute that the heat from that refrigerant into the home, and that's how you provide heating in the winter. Once it's gone through that indoor coil, it returns to a liquid state, passes out of the home back into the expansion valve, where it's turned back into a low pressure liquid, and the cycle starts again. That's how heat pumps work in the that's how heat pumps work in the heating system. In cooling mode, it's basically the same system, but it works in reverse. The refrigerant will go into the indoor coil in the low pressure, low temperature liquid. That's where it will absorb heat from the indoor air, and then that will be removed to the outside through the outdoor coil. So that's one of the common misconceptions, is we don't create cold air with these systems. We just remove the heat from the indoor air. This is an all-electric system here. The only energy it requires is to operate the compressor, to compress the refrigerant and create that high temperature refrigerant that gets transferred inside for heating. So with that understanding, the big thing we have to look at, especially for the residential heating and cooling, is how does this compare to a furnace, and where do we see these efficiencies? So when we're looking at a furnace, a typical ducted furnace like we see down here, this relies on the combustion of some form of fossil fuel. And when we look at this, this has a efficiency rating known as the AFUE, or the annual fuel utilization efficiency. And basically, this is the percentage of fuel that's converted into heating output into the home. Basically, it's a metric of how many kilowatts of natural gas you put in versus how many kilowatts of heating do you get out. And typically these start at about 95% efficient, anywhere down to 80% on a lower end model, and they typically lose some of this efficiency throughout their life cycle. With a heat pump, what we look at is the coefficient of performance. And what this metric refers to is how many kilowatts of heat, how many kilowatts of heat are produced versus how many kilowatts are needed to operate the compressor. So as we said in the previous slide, this compressor is it's an electric compressor. Once the vapor goes in there, it's all compressed, and that's what creates the heat for the inside. So you're not burning anything here where you're losing some to heat in the outdoor, you're just operating it mechanically. Because of this, we're able to transform 1 kilowatt of energy used to operate this compressor into about 3 to 4 kilowatts of heat into the inside environment. So what you realize with these is about a 300 to 400% realized efficiency. And that's what you get at about 8 degrees C. This COP metric for heat pumps will drop off as your outdoor temperature gets colder, because you are relying on refrigerant absorbing heat from the outdoor temperature. So at minus 15 degrees Celsius, there's less heat in the outdoor air than there is at 8 degrees Celsius. So because of that, the compressor has to work harder to produce the same amount of heating output, which is why you see your COP drop from 3 to 4 at 8 degrees Celsius to around 1.5 to 2.5 at minus 15 Celsius. There's not as much heat in the outdoor coil. The compressor has to work harder to maintain that heating output. So that's what we call the D rating of heat pumps here. Now, that's how air source heat pumps work. One of the big misconceptions is how they function in cold climates. And when we talk about that, we really need to talk about it in terms of the heat pump as a whole, looking at both the performance, the COP, and the cost to the end user. So first and foremost, when we look at the capacity of a heat pump, you typically will see a chart like this, where you have a maximum capacity and a rated capacity. The maximum capacity will show you the maximum amount of heating output that the heat pump can perform, if the outdoor compressor is running on full speed all of the time. It'll also show you the rated capacity, which is a more realistic measure of how much heating output that heat pump will give at any given temperature. The way I always think about this is with heat pumps, they have what's called modulating technology. So they don't run as a on or off system. They can run at 10% of their maximum capacity, 20%, 30%, whatever is required to maintain the indoor temperature. So if, for example, if the outdoor temperature is 15 degrees and you have your home set to 21, your heat pump will not be running at a max capacity. It'll be running sort of in the 40 to 50% range, which is very efficient. And that's why you see those high COPs. As your outdoor temperature gets colder, typically you'll see your heat pump will be running at more closer to the maximum capacity because it will need to keep up with the demand of the indoor unit. So here we can see our rated capacity at 8 degrees Celsius is around 24,000 BTUs. This same heat pump at minus 15 Celsius will still produce 24,000 BTUs of heat. So the performance of these at cold temperatures is very similar to them at milder temperatures. You'll still get the same heating output, but the other piece that you have to look at when you're looking at these is the COP. Oh, excuse me. So like we mentioned, the COP, it's a metric of how much energy that the heat pump is using to produce this output. So as you see, as the outdoor temperature gets colder and colder, the COP decreases because now the heat pump and the compressor is requiring more energy input to heat that refrigerant before transferring it to the indoor fan coil. This is where we really have to look at, does a heat pump make sense, both as a contractor as in a homeowner? Because, you know, where I live, I'm based in Ontario, we have fairly cheap natural gas. And as a heat pump loses its efficiency, this now starts to cost me a lot more because my electricity is a lot more than my gas bill. So that's where you have to kind of find this switch off here, because typically what we see with the heat pumps is the outdoor air temperature, as it decreases, the capacity of the heat pump remains the same, but the COP will drop. And that just means that the heat pump is working harder to maintain that capacity, which means that the running cost and the electrical requirement will go up. So for homeowners, you could be kind of shocked on your first winter with an all-electric system that your heating bill or your electricity bill has gone through the roof because your heat pump has to work a lot harder to provide the heating for your indoor environment. And that's kind of where we get into the solution sets here today, and we'll go through these now. The first one that we have is our hybrid electric system. This is really our stepping stone to electrification here. Excuse me. And the way this system works is it's a three-piece system. It comprises of an outdoor heat pump unit here, and then that's connected to a refrigeration A-coil inside. This refrigeration A-coil is very similar to a typical central air system or air conditioner that will be ducted into your home and sits above a new or existing furnace. And so the way this system works is this will be integrated with a smart thermostat that can link into the outdoor unit's outdoor ambient air temperature. And what happens here is at a certain preset temperature, the heat pump will turn off. And for the cold weather heating, you'll rely on your furnace to provide the heating. The reason we do this, we set this up like this, is for a few reasons. First of all, as we just discussed, the heat pumps do lose a little bit of their efficiency as we get into the colder climates or the colder outdoor weather, which makes their running cost more costly to the homeowner. When we switch over to the furnace, you have that natural gas as a backup heater, it's a more cost-effective way of heating your home in the dead of winter. So, December, January, February. Outside of those months, in the heating season, or in the milder temperatures, kind of between -5 and up, the heat pump will run where you're realizing, a COP greater than 2, so 2.5 to 3, and that will provide the heating to the home. This will also, when we reverse the refrigerant cycle in the summer, provide high efficiency cooling to the home as well. So this one unit can do both the cooling in the summer, the heating in the shoulder seasons like your spring and fall, and then we have the backup heating there to provide heat in the winter. In terms of this system, the pros of the system is you're basically maximizing the efficiency of both heating systems, whether it be the heat pump or the furnace. Like we see here, this red line here, that is our cutoff temperature, where we switch over to the furnace. So you have your high efficiency heating during these mild peak seasons. You also have your high efficiency cooling. It's a higher efficiency compared to your traditional top discharge condenser that you see. And so you're maximizing your efficiency there. And then below this 5 degrees Celsius, you switch to your backup heating. And basically what this does is to minimize the running cost to the homeowner. The other piece of this system that allows it to be sort of the stepping stone to a full electrification is this reduces strain on the electrical grid during most of our peak seasons here. This is very important, especially with the prevalent, as we see the growth of electrification in residential heating and cooling, as well as the electrification of vehicles. So at -25 in January, when I'm trying to heat my home on an entirely electric system, while my neighbor's charging his electric car, my neighbor on the other side is also charging his electric car and has a heat pump too. The strain on the electrical grid becomes very large, and the BTU output is not in a spot right now where it can be fully supported in those cold months. So we have to integrate this with some form of backup heat. This is one that maximizes comfort and cost savings for the homeowners. In terms of flexibility, we do have these systems are typically universally compatible with new or existing furnaces, as well as new and existing ductwork. So it's a really good solution for existing homes. Like I said, we do need to retrofit about 75% of our current homes across Canada. And this is a really easy way where you can remove a air conditioner, a central air conditioner, and replace it with a heat pump to provide heating and cooling. The other benefit of these is if you have a newer, higher efficiency furnace, that's not something that needs to be completely replaced. It can simply be added on to by this system here. So they are compatible there, as well as moving forward with builders. Typically, want a slower moving industry when it comes to reacting to change. This allows builders to use their traditional ductwork, a very familiar concept, proven concept in North America, and we can fit this system into that traditional ductwork there. These are also eligible, depending on the certain model and the specifications, they are eligible for the Enercan Greener Homes program, which is a program that is driving homeowners to be proactive about energy saving retrofits. John, I don't know if you want to hop in here and speak a little to that program and the way you've seen that develop.
Yeah, I definitely love to jump in. So yeah, that's a great explanation, Will. I think back to just 2 short years ago, and I joined the team at Nordics, HVAC equipment distributor, but more importantly, we're a heat pump house. We sell heat pumps. And in theory, it should have been pretty easy to sell these things. We've got the technology, as Will just explained, the technology's come a long way. We have the Greener Homes grant that's going to drive sales towards these heat pumps. And Nordics, we've teamed up with some great manufacturers like Panasonic. So we have the equipment, we have the grants, and we're ready to go. But pretty quickly, I thought about it from, as a heating contractor. In 15 years as a heating contractor, hundreds of forced air systems that my company installed, I can confidently say I installed 0 heat pumps during that time. And the reason is, when I got into the industry a little over 20 years ago, I married into the industry, and my father-in-law, went to work for the family company, and he said, "Oh, we don't do heat pumps in Ontario. They don't work. They don't create heat." And you know what? 25 years ago, they didn't. But the problem with heating contractors is we get very focused on doing something very well, and it takes something pretty extreme to make a heating contractor change. So I took that anecdotal training with me through the next 15 years of my life, and not realizing that the heat pump technology has advanced, that it is a viable option for the Ontario market. So when I joined the team a couple years ago at Nordics, I said, okay, we have the equipment, we have the partnerships, and we have the grant. But what are the real challenges here, and how are we going to drive heat pump sales, and how are we ultimately going to be successful at this? And we realized one of the first challenges was the Greener Homes grant itself was very difficult to navigate. I tried it as a homeowner, and I tried it as a heating contractor, and both times I was like, oh, it's difficult to navigate. The registration process was a little bit wonky. And then you couple that with some skepticism on the part of the contractors, and we're like, okay, well, what's the next step here? And I realized that if we were going to be successful, it was going to be through collaboration, training, education. So what we did, we teamed up with the manufacturers, and I'm sitting in our training room at Nordics right now. So we started doing technical training sessions to get the contractors comfortable with the technology, get rid of those sort of, those misconceptions and myths that are out there that heat pumps don't work in Ontario, because they do. Then we teamed up with a really good energy auditing company, Energy Advisors, which is the Home Inspectors Group. And that really was the next step in the evolution, in that we started doing training sessions in this room for contractors on the Greener Homes grant, how it works, how they can confidently explain it to their homeowners, which will ultimately lead to the sales, and sort of usher in the change. So that's great. And we did that. We put hundreds of people through this training room, technical training sessions, Greener Homes grant training sessions. And lo and behold, we see the change, and we saw the success, and we saw the numbers. And now it's just sort of watching the evolution of the Greener Homes grant as it changes. At the beginning of 2023, they streamlined the process. So that's great. So we did more training. We got the guys back in here, and we trained more contractors to explain, okay, here are the changes. Here's how much easier it is to drive the sales and get these things done. And then I guess it was probably June 1st when we really realized the full potential, in that the Greener Homes grant now included what we call standalone. So that's going to be full rebate for a heat pump and a coil with any furnace. That could be the existing furnace or a new furnace, but it doesn't matter. At the beginning of the program, a couple of years ago, contractors had to put in heat pump, coil, and a furnace, and those 3 pieces of equipment would qualify for the grant. But homeowners with a 3-year-old furnace and a 20-year-old air conditioner didn't necessarily, it didn't make sense to get rid of an existing piece of equipment in the furnace that was, relatively new. But as the Greener Homes grant expanded, and now we have, like, for instance, Panasonic, we have standalone options that qualify for the full rebate amount from 1.5 ton all the way up to 3 ton that qualify for the full rebate. So really the key to understanding and driving the sales is really making the contractors comfortable with it technically and on the grant side, because they're the ones who are explaining it to the homeowners. And if they can confidently do that, then they can close the deal. And yeah, we've seen from a guy who didn't install heat pumps, I was even one of those guys who was skeptical about it up until a couple of years ago, to now seeing the full potential and really being proud of the work that we're doing and the successes we're having. Yeah, it's an interesting time to be in the business for sure.
And we're glad you finally seen the light, John. So that's the hybrid electric system as we're calling it. The next piece, and depending on where you are in the country, this is what we're calling the future today, is the whole home all electric system. These are very popular already in the Atlantic region, where typically they don't have natural gas connections, and they are using oil, which has become more and more expensive over the years, and why people are tending to move away to these all electric systems. This is fairly the system. It's made up of two pieces: the outdoor heat pump unit here, and then the indoor air handler here. This will replace in your mechanical room both the furnace as well as your central air conditioner if you have one. And what happens here is, in the bottom there is a refrigeration A coil. That's where the heat transfer will occur. And then the other piece of this here is this has a built-in blower. The hybrid system we just showed you relies on the furnace's blower to distribute the air throughout the home. This has it built in here to distribute itself, so it's a one-stop shop. It also has up here a optional auxiliary heater strip. So this is a electric resistance heater that is installed in here, that's activated when there's a differential of between your actual indoor air temperature and your thermostat set point. So when that drops to, I believe it's a 2.5 degree difference, this auxiliary heater will come on to provide additional heating to the home and restore it back to your set point there. This is a great system. It's very easy for builders, contractors, mechanical contractors to retrofit a furnace as well as a central air conditioner to one of these systems. It just needs to be connected into the ductwork by sheet metal and sealed in like that there. You can also integrate these with ERVs, which is to meet any fresh air requirements that are rapidly becoming part of the code. So it's a good way to get ahead of the game and also have a fresh air supply into the home all in one. Again, this is an all electric system here. So the drawback on these, especially in areas like Ontario, is the cost of electricity in the winter, where these are working harder to provide electricity or provide heating and cooling, and they will be more costly to the homeowner for running. In terms of the grant eligibility, which is a cross-Canada program, I think we've already touched on it here. These systems typically are fully eligible as a retrofit of a furnace and an essential air conditioner there. So this is going to be sort of the next step in where we go with our electrification and decarbonizing residential heating and cooling. So I think we got through this a little quicker than was expected. That brings us to the end of the slides, and John and I are both here for questions if there are any.
Oh, I see that Mark added in the chat there, Steve Ramul from the Home Inspectors Group. I actually forgot he's speaking later today. I think anyone and everyone should get on board with that one, because Steve, he was a massive part of sort of opening up my eyes to the potential of the Greener Homes Grant and really explaining to me and my team how it works. So yeah, that's definitely, I strongly suggest everyone jumps on board with Steve's session there. One other thing I wanted to mention, Will, and you had brought up the ERVs. It's funny too, because the other, as more of these systems are going in, I think what we'll see are, some of the impacts on the air quality in the homes. And we're already getting that feedback from last winter. But for instance, with these systems, a lot of contractors are still installing them with a typical flow-through bypass humidifier. But what they're finding out is the humidity levels in the homes are dropping, and the air quality is not where it needs to be. And the reason for that is the lower plenum temperatures that the heat pump. What we're seeing is a lot more guys are realizing, okay, we should be putting an ERV into the home instead of an HRV, a good cold climate ERV, but also steam humidifiers, and even possibly putting in dehumidifiers, central dehumidifiers into the system as well. So that's one of the impact we'll see down the road as more contractors, they're putting the systems in, they're getting comfortable with the heat pumps, but we also have to be pretty cognizant of what the impact of the air quality in the home is. And that'll be something, that'll be the next step in the evolution and the training and the education that we're going to do here, which is to say, okay, here's the full package. You should be putting these systems in and going back to put in steam and maybe upgrading the HRV to an ERV, which is going to do a much better job of maintaining the humidity levels in the house. So again, really interesting time to be a part of the industry, that's for sure.
John, there's a question here I just seen in the Q&A about sizing for the cold climate heat pumps. Could you speak to that a little?
I think one of the things, one of the misconceptions, one of the misconceptions is that you have to oversize the heat pump. And what we're finding is with the hybrid systems where you have the natural gas backup, you don't really have to oversize it. What we're told by the technical trainers from the manufacturers is you should size it for cooling. You're never going to have a shortfall on the heating side. You've got that, in the Ontario market at least. Sorry, I should remember we're not, we're speaking to other places, but if I speak to the Ontario market, the bulk of what we sell right now is the hybrid system. So it's going to be natural gas furnace or propane as your backup heat source. So with the systems we're putting in now, they just, basically we say size it for, if you're taking out a 3-ton air conditioner out of the home, put in a 3-ton heat pump, keep the furnace sized accordingly. And again, you're never going to have a shortfall for heat because you do have that reliable backup on the gas side. Because I think just to add to that, because what you don't want to do is grossly oversize, and then the ductwork in the home's not going to be large enough to accommodate the airflow.
Mark, I've seemed to have lost the chat. It's giving me a red not authorized sticker. So I can't see if anything's going in there.
Okay, so I can jump in if anything goes on. I don't know why you're getting that, but I asked a question actually in the chat because I was curious. How important is it for the home to be really airtight? Like, if it's not, like, do you need to improve the tightness of the home before a heat pump can work really well?
Yeah, it's definitely going to work. And part of the Greener Homes Grant is tightening the home and upgrading the insulation. With the Greener Homes Grant, it tops out, the federal portion of the money tops out at $5,000. But the nice thing is, and again, this goes to the education of the homeowners, while your rebate amount tops out at $5,000 federally, you can borrow up to $40,000 interest-free to be paid back over 10 years for other upgrades to the home. So that's the other thing, and Steve will speak to that, Steve Ramol, on his session. But that's what they're hoping to do is if you're getting the grant process done, you're putting in the heat pump, great, you're going to top out and get your $5,000 back, but probably a good time to upgrade insulation and ceiling and windows and things like that, and take advantage of the
I think John just froze. So
okay, I wasn't sure if it was John or me. The other thing I'll add on the sizing and the tightness piece is for new builds, because of the tightness and the standards that are now being built to, it does make heat pumps a much more viable option. The other piece with them is when you are looking at a house with air leakage and a lot of heat loss, that all comes back into a sizing piece as well. And we need to make sure that people are doing air tightness and sizing calculations prior to recommending a size. But with the heat pump it is able to run at a constant rate below maximum threshold. And this is kind of it's almost similar to thinking about the fuel efficiency of your car on the highway, where it's just going at a constant rate, as opposed to the fuel efficiency in town where you're stopping and starting. With traditional HVAC systems like a furnace, that's an on-off system. It's a one-stage heating. With most heat pumps, you do have a variable stage. So what happens with that is you can have a constant input of 70%, which will maintain the temperature of the home. It will continuously provide heat even if there is air leakage, and pieces like that. So it's a very efficient way to operate, as opposed to a furnace where you have to turn on, bring the house up to the temperature, and then you wait for the house to go back down to a few degrees below your thermostat set point, and then it comes back on again. You lose a lot of your efficiency there. And you also are in an environment where it's constantly changing the temperature and is not always at your set point. So in terms of a comfort piece as well as an efficiency piece, the modulating ability of the heat pump does a very good job of maintaining a stable temperature in the home while operating at a much higher efficiency than your traditional on-off systems.
all right, that's great. Because that's something I always wondered about. Any other questions for Will? I think John's probably going to try to get back in here. I think he popped out as he froze.
Yeah, he said he'll be back. He'll be back soon, but not sure.
So. Give another minute and anyone has a question. But if not, we could end the session a little bit earlier and have a little break before I think our next session is speed meetings, which will be a lot of fun. I'm excited about those. So
perfect. Well, no, that sounds good, Mark. Thanks for having us today, and everyone, thanks for your time. I hope you learned something and enjoy the rest of the sessions coming today.
Well, and I want to thank you, Will, and John too, even though he's not here anymore now. But no, very informative session, and I really appreciate you joining us today. So thank you so much.
Yeah. Again, thanks for having us. Appreciate it.
Okay, then I will end the session then, and then if you can hang out in the lobby or the lounge and do some chats, connect with people. Please join us for the next speed meeting session, the first speed meeting session, and it will be a lot of fun to meet some new people. Thanks again, Will. Appreciate it very much.
Thanks again. Have a good one.